So, okay, then we're going to start talking about bounding the number of integer and rational points on transcendental curves. So let's start very classically with the theorem of Yarnik. So to start this whole business off, it says the following. So let's see it be a circle of radius n in the plane, r squared or whatever. Then the number of points on C, which are integers, is bounded above by n to the 2/3, completely uniformly. You can do better, of course, but let's go to the proof. So the idea is very simple. So here's our circle C, and we're going to break it up into arcs of length n to the 1/3. This is theta. This is theta plus n to the 1/3. And we're going to argue there's at most 2 points in each arc. Okay? So suppose you have 3 points in the same arc. Let's zoom in. Three points in P1, in P2, and P3, all of which are integers. Then if you look at the triangle formed by these 3 points, this is the triangle T, then you give you the area of T. On the one hand, this is a non-degenerate triangle, because you have a circle, and the coordinates are integers. So the area has to be half a non-zero integer. So it's at least 1/2. Okay? Because it's sort of this vector dot this vector divided by 2. So it actually is half integer. On the other hand, this is equal to the first side length times the second side length times the sine of this angle here. Let me call this angle, I don't know, tau, times sine of tau over 2. Right, this is the area formula for a triangle. Now these 2 side lengths are at most n to the 1/3, and the angle is at most n to the 1/3. And so this is up to a small constant. I guess sine x is less than x. This is actually less than or equal to n to the 1/3 times n to the 1/3 divided by n to the 2/3, right? Because this arc length n to the 1/3, the angle here is n to the minus 2/3. And so if you pick this constant of n to the 1/3 small enough, you get something which is less than 1/2. This is the contradiction. Okay? So that's the proof. Any questions? So this is the basic idea this whole thing will be based on. Is that on the one hand, if you take a triangle with integer coefficients, which is non-zero area, has area at least 1/2. On the other hand, for geometric reasons, it has to have area less than 1. So area, less than 1/2. Okay. So sort of similarly, you can do the following thing. You can say that, likewise, if gamma in R squared is a C2 compact curve, and the number of points in T gamma, which are integers, is bounded above by T to the thirds, so for any T, just breaking up using small segments on gamma and then scaling them up. Okay, so this is Yannick's idea. And so Bombieri and Bila had the idea to apply the same argument, but not to triangles, to apply to higher dimensional simplices. Okay, so the idea will be the following. So suppose gamma in R squared, let's for now say it's real analytic. And let's say it's not algebraic of degree less than or equal to d. Okay, so it might in fact be algebraic, but if it is, the degree at least d plus 1. So what does it mean? That means that the monomials x, y, dot, 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 x to the I, y to the j, so this sort of monomials of degree d, there's like d just two monomials over here, are independent on gamma. Not sort of pointwise, but there's no actual combination of them advantages on gamma, because if there were, they would give you a degree d polynomial advantages on gamma. Okay, so then the idea is the following. What you do is you take gamma and you embed it inside R to the power of, so let me actually be careful here. So it's like d plus 1 choose 2 minus 1. Taking all the non-constant monomials over here, leaving out 1. So this, yeah. we embed it here. And the idea is that on R to the d plus 1 choose 2 minus 1, we do the same game we did over here, only instead of triangles, we use d plus 1 choose 2 d plus 1 choose 2 minus 1 dimensional simplices. Okay? And the hope is if you sort of, the more, it's not a priori clear, we'll sort of go through it, but the hope is that the more guy you use, sort of the better inequality you'll get. Okay. Okay, so before doing the sort of general case, let's do a simple example, or a simpler example. So suppose gamma is so let well, maybe. So maybe let's do the following thing. So just to do a volume computation. So suppose you have, I don't know why I made an inflection point. So suppose you have y equals f of x, where f is real analytic, around some point x equals p0, well, x equals p, y equals f of p. And so let's see what happens when we take a small interval around P, pick a bunch of points there, embed them, and take their volume. Okay? So let I, in, let's call this gamma. So in gamma, be, let I be the interval P minus epsilon to P plus epsilon. And let's pick a bunch. So here's like I. Here's the lift of I. This is f of I. Now let's pick a bunch of points in I. So pick x1, x2, xd in I, where d is d plus 1, choose 2 minus 1. And now consider the simplex in R to the D. Let's take this to go to R to the D plus 1 actually. One of this makes one to make a simplex. So consider the points in R to the D whose vertices are the points xi to the a times f of xi to the b, one is at most a plus b is at most d. So we're taking every single point and we're embedding it via the monomials that we talked about. Okay? And so I is varying here. Questions? Fine.
Big D is supposed to be the number of monomials in the middle.
I'm sorry?
Big D is supposed to be the number of monomials.
Big D is number of monomials, yes. Did I mess that up? Oh, is it one? Is it this maybe? Is that big D? I think that's probably better, right? So let's see. So big D is, you have these two, you have these three, and at the end you have D plus 1, guys. Yeah, so it's one bigger. Sorry. Thank you. Yes, you're totally right. Mm-hmm. So here's a simplex S, let's say, in R to the D, whose vertices are these. Okay? Okay, we want to understand what the volume of S is. Now, because F is remoanalytic, so if we write Xi is P plus epsilon I, where epsilon I is most epsilon, we can write f of xi as, we're going to expand the power series basically, so a sum I equals 0 from, n equals 0 to infinity of the nth derivative of f at p divided by n factorial times epsilon I to the power of n. So in other words, all of these coordinates we can think of as power series in epsilon sub I. Okay, where epsilon sub I is some small guy. So let's call this point something. Let's say R of x sub I. Then the volume of S is equal to the determinant of the matrix M. I then put a vector here to remind you that this is a vector point. It's got a bunch of coordinates. So the determinant of R of xi minus R of pi divided by n factorial in absolute value. Okay? In fact, it's probably better, instead of the simplex, consider the parallel pipe, but by analogy, we'll just consider the simplex. This familiar to everybody? If you take a triangle with dot product the sides and divide by 2, in general, you take the determinant of the n vectors and divide by n factorial. Okay. I'm sorry, I screwed this up a little. Sorry, so I did want d points. That's right. And I want the simplex whose vertices are this, and also R of p. Yeah, let's set it up this way. Yeah, it's going to include the center point, the other points. Okay, so we want this. Yes, thank you. That's not the real numbers, it's R. Yes. Okay, but now, so now R tilde, let's like write T of epsilon I as R of xi, which is just P plus epsilon I. Minus R hat P. So then this guy is a power series. In epsilon I with 0 constant term. Okay. And so the volume of S treated as a power series in all the different epsilon i's. So let me write this as a function of epsilon 1 through epsilon d vanishes whenever epsilon I is equal to epsilon j. So I not equal to j. But because we can, this thing is also a power series in the epsilon I, we get the product of epsilon I minus epsilon j, I not equal to j, times some other power series in the epsilons is equal to the volume of S. Okay? Okay, so now epsilon I minus epsilon j is bounded above by twice the original length h over n, which is 2 epsilon. And this f guy is big O of 1, uniformly bounded, it's a convergent power series. And so the volume of S is bounded above by a constant times epsilon to the power of the number of terms here, which is v choose 2. Okay?
Sorry, what's the volume S and then the subscript epsilons?
Well, so I want to think of volume S here as a power series depending on the varying parameters epsilon 1 through epsilon d. That's all I mean by this.
Oh, okay.
Yeah. So I want to do this in order to sort of write this as the identity of power series. Okay. And so probably you can see that it didn't actually matter that much which monomials we took in bed via. Monomials are the same, from the same kind of thing, but we're true. Okay. Okay, so now suppose that, as before, so suppose gamma inside R squared is real analytic. And transcendental, so it's not contained inside any algebraic thing. So then claim, and let's make it compact as well. What they really mean is that gamma is some real analytic thing, and we take some like compact piece of gamma. So I want it to be analytic at the endpoints as well, make this argument work out. The claim, and this is a Weberian pillar. And it was actually proven later using a different method by Alkies. But we're following Weberian pillar very solidly. That if you look at the number of points inside T gamma intersect the Z squared, this grows slower than any power of T. Okay? So this isn't actually the version we want, but let's stick to this version for now. Yeah, the proof idea is very simple. It's literally follow this computation, break up into as small intervals as we can, do a computation, and sort of and get a bound. Okay. So let's prove it. So let sort of I be a, so let me say I, let's just say I and gamma be an interval of length epsilon. Let's see if there's any. Length epsilon. Let D be some positive integer, and D be, what do we decide? D plus 2, choose 2 minus 1. Is that right? I think that was right. If D is 1, you have 2 points, which is good. Sorry, D plus 2 minus 2. I think this is right, but if it's wrong, then I apologize. It's what it was before. So do this and pick this many points, and let x1. Let me write the following. Let me write x1, y1 through xd plus 1, yd plus 1 be inside I. Okay? And suppose that T, so that Txi, Tyi are also in Z squared. So we're sort of blowing up gamma, taking a relatively small arc inside the curve, and we're assuming we have this many points on, integer points on. Okay. Okay. So now let S be the simplex whose vertices are so Txi to the power of I plus to the power of a plus b. Sorry, txi to the a, tyi to the b, or a plus b between 1 and b. And so these are inside r to the d plus 2 choose 2 minus 1. Again, we have d plus 1 integer points. Yeah, that's correct. Okay, so the idea is very simple. Again, on the one hand, we have integer points. So the volume is to be either 0 or 1. Well, either 0 or at least 1 over d factorial. On the other hand, we'll try to make the volume as small as possible. So note that like the scaling is not like playing against us in a pretty serious way, because these t's are also growing pretty quickly. Okay. Okay, so on the one hand, so if volume of S is not equal to 0, then the volume of S is at least 1 over n factorial. So we'll deal with the volume of S equals 0 case later. Now let's assume it's not.
N factorial is d factorial.
N factorial is d factorial. It's actually, yes. Sorry, and this is just d minus 1, right? This is just d. Yeah. Okay. It's d factorial. On the other hand, let's compute the determinant geometrically. So before we scaled, we had an upper bound of epsilon to the power of was it d choose 2? Is that right? Yes, f bar of d choose 2. Okay, but now we're scaling the coordinates, so it's going to be bigger. So let's keep track of the scaling. So this isn't quite what I'm about to do. I'll do it more legitimately later. Now let's pretend that each scaling just increases the volume by that much. That's not exactly what happens because the coordinate gets stretched in different ways. But so pre-scaling, volume was a constant times epsilon to the power of d choose 2. Post-scaling, we get the volume of S is at most what it was before times the sum over a plus b is at most d of t to the power of a plus b. This is how much the ab's coordinate is increased by. Okay? And you can actually compute this correctly. We're not going to do that. We'll just give an upper bound for it. Each of these terms is at most d. There's capital D many terms. I'm just going to write at most this times either little d times big D. Okay? Sorry? Sorry, the sum should be at the top. This is the product, yes. Thanks. So again, it's not totally legit, the computation I'm doing. You can't just do this kind of thing, but it works out all right. Okay. So therefore, if epsilon is at least t to the minus d choose 2 later, minus d choose 2 over little d times d. Volume of S must be 0. Sorry, the vice versa. Minus d times d over d choose 2. Right, epsilon's at least as much, then this expression becomes less than 1 over n factorial, and then combined with this, 1 over d factorial, combined with this, you get the volume is 0. Okay? So I don't, maybe somebody does. I personally don't have any insight where you get something sort of better as little d is growing. It's not entirely clear to me. I mean, it has to do with the fact that there's quite a few monomials of every degree theory. If you took monomials, one monomial of degree I for every I, you wouldn't see any improvement. But somehow, because you have this combinatorial growth, you do see an improvement. I don't have much intuition for why that happens. But it does seem to happen. So corollary. So if you look at any d plus 1 points, in ti of z, we call them, so let's call them like p1 through pd plus 1. Then the rank of the matrix R of pi and the rank of the matrix R of pi minus R of p1 is what I mean to say. Is at most d. Right, so if we just look at the R is the one from before, if we just look at the d vectors that we get to find the simplex, it must not linearly span. If it linearly spans, we determine it would not be 0. But it is 0, and so this rank is at most d. Okay, but this is true for any d plus 1 points, which means if you look at all the points and you form this matrix, which is no longer square, the rank of that non-square matrix is also at most d. So, therefore, if you let P1, Pn be all points in Ti of z, Ti of z, the rank of R of pi minus R of p1 less than or equal to n, I plus 2 to an n. This is at most d. Okay, but what does this mean? This exactly means that the columns all have a fixed linear relation, because this is a d by n matrix. A d plus, sorry, this is, make no mistakes. This is d minus 1. This is d minus 1. This is a d minus 1 by n minus 1 matrix. Now, this is a d by n matrix. So this matrix here is d by n. and it ranks at most d minus 1, which means the columns have a fixed relation between them, which means there is a degree d polynomial, or degree d curve, C, such that the integer points on Ti are actually all inside C as well. Right? This is a fancy way of saying that if any 3 points lie in a line, then in fact all your points lie in a line. Likewise, if any d plus 1 points have some degree little d polynomial going through them, degree little d polynomial going through them, then all the points have degree little d polynomial going through them. You can just check it with this rank condition. Okay? So therefore, the number of points on T gamma, which are integers, is by constant bounded above by, well, how many intervals do we need? We need this many intervals, d big D over d choose 2. And for each interval, how many points do we get? Well, we get the supremum over degree C equals little d of the intersection of T gamma with C, but we can just scale C down. So this is the same as gamma intersect C. Okay, now d is quadratic in little d, so this is like 1 over little d. Right, so recall d is d plus 2 choose 2 minus 1, which is what? It's like d squared plus 3d over 2. And so as little d goes to infinity, this guy here goes to 0. So we're done as long as we can show that this guy is uniformly bounded for each little d. So claim the supremum is finite. Okay. So it shouldn't actually be a surprising claim, because each one of these is finite, and degree little d curves come in a compact family, just the projective space of the coefficients. So in fact, there should be some trivial reason why this is true. But I don't know this trivial reason. I tried for a long time to come up with one. And I can't. So actually first let me point something out. So before we prove the claim, just as an example. So for this, I have 5 minutes left. Okay. Good. Good. So As an example, I really need gamma for this to be real analytic, and like everywhere, and not just smooth. So what you can do is you can let y, you can look at y to be sine of 1 over x times e to the power of minus 1 over x squared. This is some graph. And what does this look like? Well, sine 1 over x looks like this. Right, it jumps back and forth between minus 1 and 1, faster and faster. But we're multiplying it by a function which decays super quickly at 0. So this looks like something which sort of does this, and then it starts growing again and oscillating. So this guy is actually C infinity, and it's also real analytic everywhere except for 0, where it's also C infinity. Okay? And excuse me. And nonetheless, the x-axis crosses it infinitely many times. In fact, I've made it so that all these points are actually 1 over an integer. If you do 1 over this guy, you get a whole bunch of integers. So it's sort of, I don't know. You have to be a little careful with when this kind of thing is true. And this kind of nonsense is exactly the kind of thing definability is going to rule out in general for us. Just so we're aware. We don't want that. Okay, but right now we're in the real analytic world, so things are a little simpler. So what you do is you say, so suppose not, then what you do is you expand gamma into a complex analytic germ. Gamma sub c in c squared. We're actually a power series somewhere, so we can actually expand it inside the complex numbers, just by considering the power series with complex number coefficients. And so assume so intersection of C1 with gamma, Ci with gamma is bigger than I for every I. Okay, by putting these in the compact family, we can assume the Rho log the Ci converge to some curve C, making all the coefficients converge. So then the point is that if you look at the actual multiplicity, intersection multiplicity of gamma with C, where now you count each points with a complex analytic intersection multiplicity. So this bounds above the supremum, the lim sup over I of gamma intersect the C sub i's. Okay? So it's like a bunch of, so what's your enemy? Your enemy is that you have a bunch of point intersections, but in the limit they all converge to a single point, 0 or something. But if you actually count the intersection with the multiplicity, that can't happen. You have this one. And so, but this actually bounds just the lim sup of just the size of this. The multiplicity every point is at least 1. Sorry, gamma sub c. You have to keep track of the holomorphic guys. Okay, but this is less than infinity. Just Okay, this is the only way I really know to see it without doing a lot more work, even though it's rather simple lemma. Okay, so that's the proof of this fact. So now if we wanna make what we're really after is two improvements, well, three improvements, but we'll focus on two. One is replacing the integer point count with rational points, which actually isn't such a big deal. The same proof essentially works, just keep track of denominators, and that gives you a slightly worse lower bound, but it's still sufficient. And the other is we've been dealing with the easy case where gamma is sort of smooth and compact, which makes uniformity bound really easy. If gamma doesn't break, then it actually gets quite long, and you have to make this argument somehow uniform along all of gamma. So we'll focus on that next time.